Hello, today we talk about the stability of the different conformation of the Newman projection. There are three main ones we can draw. I start with the most stable one. Here we have a 3-carbon alcohol with the OH hydroxyl group. Let me draw in the hydrogen as well. Color code for you because I'm nice. We're going to do the line angle later on. Color code will help. The point here is the two largest group of this molecule, the hydroxyl OH and the methyl, are 180 degrees apart from each other. That is as far apart as they can get, very stable. This is the highest stability and lowest energy conformation of the Newman projection for this molecule. This example is like when you're sitting on the bus, mind your own business, and then across from you, directly in front, 180 degrees apart, there's a big fat guy decide to sit down across from you, but no problem, like very far apart, everyone stable, everyone happy. That's the anti-conformation. Now, make sure you number your carbon. I always tell the student to number the carbon. This is a 3-carbon molecule, 1, 2, 3, OH on carbon 1, and then the methylene on carbon 2, and then carbon 3, just the regular methyl. Now if we want to draw the line angle, the carbon 1, if you recall from the previous video, the carbon 1 conformation, I call this the Ginyu conformation. The two hydrogen are pointed down, so make sure you have the line angle correct. The OH on carbon 1 is up in the Newman, so make sure it is up in the line angle. I'm going to use a bit of magic over here, make this larger because I drew it too small. Now this is the power of technology. My God, I used to always draw on the pen and the paper, use ton of ink, ton of paper. Now I got the tablet, everything is so good. It's not cook, it's we're looking down C1 to C2. I did not spell it wrong. I know how to spell look. I just draw the L looking like a C, but it's looking down C1 to C2. If you look at the Newman up top, it's the C1 is the front carbon, C2 is the back carbon. Now, we want to draw in the hydrogen from the Newman down in the line angle. If you have the model in front of you, you can see this right away. If you don't have the model in front of you and your brain cannot see this, you need to build the goddamn model. And this is why I color code it. On the wedge carbon coming out at you, the wedge bond like the James Bond, that has to be the carbon on the line in the Newman. If we are looking down C1, C2, and then the dash colored carbon must be the left carbon from the Newman. There's no ambiguity here if you look at the 3D model. Now, the next level of the stability, slightly less stable than the anti-conformation, is if you rotate the back carbon. Doesn't matter, you can rotate the front carbon or the back carbon. I choose to rotate the back carbon. So now the methyl group, that CH3, is closer to the OH group. The two large groups are now slightly closer, or actually a lot closer compared to the 180 degrees apart. And then make sure you fill in your atoms. The front carbon is not rotated, so you can keep the hydrogen in the same spot. But the back carbon is different now. We rotated 120 degrees counterclockwise the back carbon. So now make sure your atoms are in the correct place. If the metal go up there, the green hydrogen must be down. And this is the 60 degree apart of the two large piece of the molecule. We call this the gauge conformation. Slightly higher energy, slightly less stable compared to the anti-conformation. This side, if you in the bus and then the fat guy decide to come slightly closer to you, sit a few seats away, not very far, not very close, he not touching you, everything is fine, but maybe the body odor start to come over, so slightly uncomfortable, slightly less stable, but overall no much problem. Now we want to draw the line angle form of this ghost conformation. Start the same, every line angle look like this, right? The carbon one still have the OH. Again, we did not touch the front carbon, we did not touch carbon one, still the same, we just rotate the back carbon. So now that terminal carbon at the end of the line angle is no longer the metal carbon 3, it is the hydrogen. If you look at the model, you can see this right away. So now the question is, where is the carbon 3? If you look at the model, you look down this model, carbon 1 to carbon 2. Cite down the bond in your 3D model that you better have built. If you don't build a model and you complain to your professor you can't see it, your professor will send you to the dean, my god. So here is the method. If you look down the carbon 1, carbon 2 in your 3D model, you can tell right away that the method from this Newman projection on the right hand side must be wedged if you look at it in the line angle. Same idea for the carbon 1. The hydrogen on the right hand side will be wedge bond like the James Bond, and then the dash coward hydrogen going away from you will be on the left from the Newman projection. Now before I get to the least stable one, I just want to quickly show that this is not the only way you can draw the anti and the ghost conformation. I just draw the small guy down here to show you example. As long as your two large groups are 180 degrees apart from each other, it is the anti conformation. Does not matter how you rotate the bond, as long as the two large groups are 180 degrees apart, that's the anti conformation. You can rotate the bond however you want. Same idea for the ghost, you can rotate the bond however you want. I would do the hammer conformation for the front carbon instead. Again, if you forget what I mean by the hammer, you can go back to the previous video. As long as your two large groups are 60 degrees apart, that is the ghost conformation. Does not matter how you rotate the bond, you can draw this multiple ways. I encourage you to go draw on your own time. Practice, student always ask me how you know, because you don't draw, that's why you don't know. You need to practice drawing. Now let's draw the least stable, highest energy conformation of this Newman projection. We need the OH and the methyl group, the two large groups of this molecule, about 0 degrees apart from each other. Now, when you build the actual 3D model with your model kit, the two large groups should be 0 degrees apart, but on the paper, on the 2D, I cannot draw them 0 degrees apart, otherwise you cannot see the back carbon, right? So I just draw them about 0 degrees apart. This you can assume they are 0 degrees apart. Now, this conformation, we call it the eclipse conformation. Just like how when the moon blocks the sun, the planet Earth where we are, we have the moon. I don't know where you are, but we have the moon. And when the moon blocks the sun, we call that the eclipse. And now here we have the OH blocking the methyl group, so this is the eclipse conformation. This is the highest energy, least stable conformation of the Newman projection, where the two large groups are right next to each other. This is like when you are on the train and then the big guy, oh my god, the other day when I take the public transportation, I take the train, because I no money, my bank account is destitute, I don't have the money, so I have to take the public transportation. And then during the rush hour the other day, this big guy sit right next to me, 0 degrees apart, maybe 1 degree apart, but something like that. He pressed his fat arm against me. I am very unstable, very high energy, very stressed out. I have so much energy, I almost beat the shit out of him. My god, that is the eclipse conformation. And then, if you want to draw the line angle of this eclipse conformation, slightly different. Again, you want the two large group to be about 0 degrees apart, so in the line angle it look like this. Make sure you number your carbon as always, 1, 2, 3.